Here we are with another statics tutorial. This one's going to be a short tutorial. This is out of the method of sections content in the Hibbeler textbooks, number 635. And what we're going to do here is we're going to find the force in members EF, CF, and BC and state if the members are in tension or compression. All right, so if you were to get this problem on a test and you saw this diagram and then you saw where it's asking for these three components here, those three forces, that should indicate to you method of sections. All right, and the reason for that is method of sections, you can typically find at most three unknowns with your one free body diagram. All right, and that's because we have three equilibrium equations. Okay, so the way we want to start off after we've already figured out its method of sections is we want to figure out where these members are. Okay, so here is EF right here, and then CF is right here, and then BC is right here. Now the goal for method of sections is to section this truss so that we go through the three unknowns. All right, so at most we can go through three unknowns. Now, can you figure out how we could section this and make that happen? Well, what if we did something that looks like this? All right, so this goes through the three unknowns we want, and it doesn't go through anything else. All right, so this is the section we'd want to make, and then we have to figure out which part to use for our free body diagram. So we can use this top part, or we could use the bottom part. Now, which one seems like it would be easiest to use, or would take less time? Well, I think the top one would be better, right? Because this bottom one, if I were to draw the free body diagram here, I've got to deal with the pin and this roller at B. I'd have to know what those forces are. So that's going to require extra work to figure that out. If I use this top section, I don't have any external supports, so I don't have to go through and solve for those. All right, so always look and see which one is going to be less time consuming. So this top one is going to be the more efficient choice because you don't have to spend your time finding the A and B reactions. Okay, so we're going to use the top section of the frame to solve this problem. So now let's draw an outline here of that top section. So it's going to go like this and then down. And then you can draw that middle part there if you want. Okay, so it looks kind of like that. All right, so here's E, here's D, you got C here. All right, so now we need to put the forces on here. Now let's start out with the simple ones. Let's start out with the external ones that are applied. So the only one on this top section is 4 kilonewtons. Okay, so we're going to put 4 kilonewtons here. Now a lot of people would want to put 8 kilonewtons. We don't want that on there though, because notice this right here is not on our top section. Okay, so this force is not in contact with any part on the top section, so we don't need to include that. Okay, so those are the only forces that we need here, 4 kilonewtons, that's it. Next, we are cutting through these members. So those members have forces in them, right? We've got either tension or compression. So we need to draw forces to show that. Now, the way I always do it is I always draw the forces going out of the section. So for this one right here, let's call it EF. Notice I'm drawing it going out of the section. And then this one right here, we're cutting through this member, so there's a force there. So let's draw it going to the left because that would make it go out of the section. We can call that CF. And then finally I'm cutting through this member right here. So let's make it go down. Let's call it BC. Okay. And the reason why I draw them going out of the section is because then if I get a positive number, that means that member's in tension. If I get a negative number, that means we're in compression. Okay, So makes it really easy to figure out if it's tension or compression. So just always draw the forces going out of the member and it'll make your life easier. Okay, so now what we're going to do is we've got this free body diagram, and let's put some distances on here. All right, so we got 1.5, we got 2 right here. And now let's look at our equilibrium equations. So I've got 3 equilibrium equations I can use for this diagram, and I'm wanting to find these 3 unknowns. Okay, so let's go ahead and start with a moment equation. Usually that's going to be the easiest. All right, so let's do that. And let's figure out a point that would be good to use. So what point do we think would be good? Well, really we have 2 choices. So I could take the moment about C. That would be a good choice, right? Because I've got 2 unknowns going through it. Okay, so that'd be a good choice. Or if I wanted, notice that this force, the CF and EF, those are going to basically both go through a point right here, which is kind of where F is on the diagram. So I could also use that point if I wanted. Okay, you could use either one, and you're going to get, the same correct results. Okay, so I'm going to go ahead and I'm just going to go and use F right here. That's just the one I picked. Like I said, you could use C if you wanted. Okay, so let's go ahead and use this point F. So now I've got a moment created by this 4 kilonewton force, and that is going to be a negative moment because it goes clockwise. So it's going to be -4. The distance to point F is going to be 2 from right here. All right, so we got 2. And then the only other force that's going to cause a moment is going to be BC. Right, so I've got BC, and for this one, if we think about holding this fixed at B and then we're pulling down, it's going to be a clockwise moment. So that's going to be negative also. And then what would that distance be? It's going to be the 1.5, right? Because we need that horizontal distance. And that's all we've got, because CF and EF both go through this point F. So we can set that to 0. And then from that we can solve for BC. So we get -5.333 kilonewtons. Now the negative tells us that we have compression. Right, so a lot of the textbooks will get rid of the negative and they'll just put a C here on the right side. So meaning it's in compression. All right, so now we've got that. And now that we know this, we can put this value up here. Notice I'm carrying that negative here. And then let's go ahead and do the X and the Y equilibrium equations. All right, so X, I've got a +4, a negative CF, and then that's all we've got, right? That was pretty straightforward there. Set it to 0, so CF then is going to be +4.00, that's kilonewtons. It's positive, so that means we have that member in tension. Right, so there you go. And then last one, the Y direction. So I've got negative EF, and then BC here is going down, so let's put negative BC, but we're going to plug in our negative value here. So -5.333. And that's all we have for the Y direction. Set that equal to 0. So EF ends up being 5.333 kilonewtons. It's positive, so that means we have the member in tension. Okay, now you might wonder how a negative indicates compression, positive indicates tension. So let's kind of walk through that before we're done. So to do that, let's look at point C right here. All right, so here's point C. Let's see, let's put it right here where we can see it. Okay, so we've got this point C. Now let's look at the members. Okay, so I've got BC, which was negative. Okay, so typically that means we're drawing it in the wrong direction, right? So if I were to draw that in the correct direction, we'd have BC going up into that joint. Okay, now remember I've got the member BC here. Okay, so it's going up into that joint. Now we also have a force felt by the member itself. So due to Newton's third law, we've got equal and opposite reaction, right? So that means there's got to be a force going in the opposite direction of this one. So now we've got that. Okay, and then we would have the same thing down here at B. So we would find, if we went through and solved everything at B, we would find that we have a force pushing up into that member BC. So since the member is being compressed, right, on each end, it's in compression. Now for tension, if we look up here at CF, right, CF was positive. So if that's positive, then this is correct. Like we drew it, it's going left out of the joint. Now the member, if we were to draw the member, we have to go in the opposite direction of this, right? So that means we're going to have a force CF that has the same magnitude as this one, but it's in the opposite direction. So notice here, if we have this on the other side, that this is pulling that member. So this one would be in tension. So that's why if you get a positive on your force components, then it's tension. If you get a negative, it is compression. All right, now that only works though if we draw the forces going out of the joint. Okay, so if you're sometimes drawing it into the joint and sometimes out of the joint, that's not going to work. But if you always draw it going out of the joint, that sign convention will hold true. All right, and it just makes it a little bit easier to figure out if it's tension or compression. All right, hopefully y'all found that helpful, and I will see you guys next time for a different tutorial.